Physics Chapter 18, Video 9, Observing the Earth. Artificial satellites have a variety of uses. Many are used for making observations of the Earth's surface for commercial, environmental, meteorological, or military purposes. Others are used for astronomical observations, benefiting greatly from being above the Earth's atmosphere. Still, others are used for navigation, telecommunications, and broadcasting. So, what happens is now many of the satellites are used to observe the Earth. We send it up into the sky and we look back at the Earth. There are other satellites which actually keep an eye open towards the outside of the Earth, into the sky, into the space, deep space. Now there is, you might wonder, why do we have to have telescopes up in the sky when we can have them here? Because it wouldn't make any difference if you keep it here on the surface of the Earth than in the atmosphere about 200 kilometers away from the surface. Because we are looking at objects which are trillions and so far away, light years away. So then why does it make any difference? The difference is the atmosphere. Looking up at the universe, looking at the other galaxies and this stars would be like looking outside through a foggy glass. We cannot see much because the fog fog reduces our visibility. So the atmosphere with all of its components will reduce the visibility for these telescopes. As a result, we have to make sure that the telescope is outside of or at the far edge of the Earth's atmosphere. Then to look, watch out for in meteorological, they predict now tomorrow it is going to rain, or you are going to this hurricane is going to hit this country in 2 days, so we prepare ourselves, right? So like that, those observations are made using these satellites, because these satellites are up in the deep sky, and they can observe, they can see what is happening down in the atmosphere. Figure 18.11 shows two typical orbits: a satellite in a circular orbit close to the Earth's surface and passing over the poles, complete about 16 orbits in 24 hours. As the Earth turns below it, the satellite sees a different strip of the Earth's surface during each orbit. A satellite in an elliptical orbit has a more distant view of the Earth. So now 18.11 diagram. So here there are two orbits. As you can see, this very close to the this satellite. It is very close to the Earth's surface, and it is going in circular orbit close to the Earth and going up and above the poles, right? So these these two types of orbit. This is the second one is in an elliptical orbit. Elliptical orbit means it goes in an in a not exactly a circle, but like an egg shaped circle is what it goes along. Then geostationary orbits. A special type of orbit is one in which a satellite is positioned so that as it orbits, the Earth rotates below it at the same rate. So that means it is kept stationary, not stationary by itself. Stationary relative to the movement of the Earth. That means when the Earth is rotating, it is also rotating at the same rate as the Earth does. I hope you understood. So now let me explain it using a diagram. So what happens is, now if this is the Earth spins around itself at a certain speed, right? If this is it at time equals t, then this position is here. Then this position will move up to this point in 12 hours. From here to here, it will go in 12 hours. right? Then it will come back to this position in 24 hours. So what happens is, um, geostationary orbits are placed uh, at a certain height to make sure that it goes in at the same rate as the Earth spinning. The Earth rotates below it at the same rate. The satellite remains above a fixed point on the Earth's equator. This kind of orbit is called a geostationary orbit. There are over 300 satellites in such orbits. They are used for telecommunications, transmitting telephone messages around the world, and for satellite television transmission. A base station on Earth sends the TV signals up to the satellite, where it is amplified and broadcast back to the ground. Satellite receiver dishes are a familiar sight, right? You must have seen those, these dialogue TV and whatever the satellite dishes. Um, you will have observed how in a neighborhood they all point towards the same point in the sky because the satellite is in a geostationary orbit. The dish can be fixed. Satellites in any other orbits move across the sky so that a tracking system is necessary to communicate with them. Such a system is complex and expensive and too demanding for the domestic market. Geostationary satellites have a lifetime of perhaps 10 years. They gradually drift out of the correct orbit, so they need a fuel supply for the rocket motors which return them to their geostationary position and which keep them pointing correctly towards the Earth. Eventually they run out of fuel and need to be replaced, right? So these geostationary satellites are not going to be very much of permanent fixtures, so they have to be, every 10 years, like they have to be, they are not exactly 10 years, every year they have to make amendments to their pathway, and they have a supply of fuel to keep them in position, and to make the adjustments, whatever the adjustments that need to be made. Then we can determine the distance of a satellite in the geostationary orbit using the equation t squared equals 4 pi squared upon gm r cube. So these equations you must understand and remember. For a satellite to stay above a fixed point on the equator, it must take exactly 24 hours to complete one orbit. So obviously that is obvious, yeah, like I explained to you earlier. We know that g equals 6.67 into 10 to the power minus 11. We substitute those values and then we will get r equals 4.23 into 10 to the power 7 meters. So that means for a satellite to occupy a geostationary orbit, it must be at a distance of 42,300 kilometers. 42,300 kilometers from the center of the Earth. So that is, you have to understand that the Earth radius is only 6,400 kilometers. So this is at least 6.6 times Earth's radii from the center of the Earth, right? The moon is just 340,000 kilometers away. So this is just really far, right? Comparatively, it's very far. So the orbital radius is 6.6 Earth radii from the center of the Earth, or 5.6 Earth radii from its surface. To give you an idea, this has been actually drawn with a measure, with a proper measure. Geostationary satellites are parked in the Clark belt, high above the equator. This is a perspective wave. The Clark belt is circular. I hope you understood this. Mostly what you need to understand is the mathematical part of it. But you need to know what a geostationary orbit is. Write down observing Earth. To observe Earth and also the universe, satellites are placed at different orbits around the Earth. Many satellites are close to the Earth, going in circular orbits. Completing as many as 16 orbits in 24 hours. When the Earth turns below it, these satellites see a different part of the Earth below it. Next, leave a line and write. A geostationary orbit is, however, a special type of orbit in which a satellite is positioned so that it orbits at the same rate as the Earth below it orbits. Leave a line and write. As a result, it remains at the same position in relation to the Earth. Leave a line and write. To maintain a satellite in geostationary orbit, it should be kept at a certain distance with the correct speed so that one orbit takes 24 hours. One orbit takes 24 hours. Leave a line and write. These geostationary satellites are mostly used for telecommunication purposes. Leave another line and write. When these geostationary satellites drift out of their correct orbit, they fire their rocket motors and return to geostationary position. Leave a line and write. We use the following equation to determine the distance of a satellite in a geostationary orbit. the equation is this equation: t squared equals within brackets 4 pi squared divided by gm close brackets r cube. Right. And then I want you to write this down. So this is the calculation that we do: gmt squared divided by 4 pi squared, g equals 6.67 Newton to the power minus 11 Newton meter squared per kilogram squared. T equals 24 hours, that is 86,400 seconds. You multiply by 60 and 60 24. And m is the mass of the earth, 6 into 10 to the power 24 kilograms. R cube is then 7.66 into 10 to the power 22 meter cube, and then you get the cubic root. You will get 4.23 into 10 to the power 7 meters. Right? You write that down and then write, as such, for a satellite to occupy a geostationary orbit, it should be placed 42,300 kilometers from the center of the earth and at a point directly above the equator. I hope you understood. If you have any questions, please raise them, and after you have gone through this video, please do question number 13 and 14 before moving on to the end of chapter questions. So to summarize what we have learned, the force of gravity is an attractive force between any two objects due to their masses. Any object with a mass has a gravity. This gravity will depend on its mass. The gravitational field strength G at a point is the gravitational force exerted per unit mass on a small object placed at the point. That is, G equals force upon m. The external field of uniform spherical mass is the same as that of an equal point mass at the center of the sphere. So that means the gravity seems to be acting from the center of that spherical mass. Newton's law of gravitation states that any 2 point masses attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of their separation. So from that we take the equation F equals G capital M simple M divided by R squared. So that is one equation that you need to by heart. Then gravitational field strength at a point is the gravitational force exerted per unit mass on a small object placed at that point. Then G equals capital G M upon R squared, and capital G always is the it has the same value, right? You have to they will give that 6.67 into 10 to the power minus 11 will be given, but it's always good for you to by heart that as well. Then on or near the surface of the earth, the gravitational field is uniform, so the value of G is approximately constant. Its value is equal to the acceleration of free fall, and you know that closer to the earth it has a value of 9.81 meters per second squared. The gravitational potential at a point is the work done in bringing unit mass from infinity to that point. Right, so that is also something that you must understand, and the equation gives you a negative value because we are talking about a reversal from the infinity. The gravitational potential of a point mass is given by phi equals negative gm upon r. The orbital period of a satellite is the time taken for one orbit, and we got an equation for that. T equals G capital M simple M R squared. So we combine them. The orbital period can be found by equating the gravitational force Gmm upon r squared to the centripetal force mv squared upon r. You can remember the final equation we obtained. The orbital speed of a planet or satellite can be determined by using v squared equals gm upon r. Then geostationary satellites are placed higher up at 42,300 kilometers away from the equator, and it takes 24 hours to orbit once around the Earth, and they are used for telecommunication, transmissions, and television broadcasting. If you have any questions, please raise them, and then after you do question number 13 and 14, please go to the end of chapter questions.